Hey class, just wanted to show you a little demonstration on how to use this PID Demo website. This is just the website. I just kind of zoomed in and make the video size a little smaller so you can see a little better. And I'll just follow along with kind of my description that's in the notes. It's kind of hard to, I guess, follow along with the typed text in the notes, so I thought this would be advantageous to give you a video. So first thing in the notes, I change a couple of values from the default. These are the default values that show up. And first thing I do is I leave KP as 1, and I change KI and KD to 0, leave the mass to 0.2, motor force limit to 1. But I want to add just a little bit of damping, otherwise it's going to oscillate forever. And so I change that to 0.01. After doing this, then I can move the car side to side using this guy, and I can put it on an angle using this guy. So I'm going to put it on a slope, and it's going to try to maintain its position on this slope. So it wants to be right where I leave this marker. And so you can see the gray line is the desired point, and the blue line is the actual point of the car, and it just kind of just scrolls and erases over itself as it moves. First thing I want you to observe is notice that it oscillated a little bit, but now it's about stopped and is coming to rest at a huge gap between where we want it to be and where it currently is. And the reason this is because we're only using a proportional controller. Our output to our motors is only KP times the error, which is this gap. And so gravity is pointing downwards, right? Or really, well, downwards, but there's a sine theta that's pulling the car backwards. And that will always be there, but our motors can only output a maximum force of this error times KP, which is 1. And because at this point that max force happens to balance out the downward pull of gravity, the cars come to a stop. If I want it to get closer to my desired set point or reference, then I can make KP bigger. So let's see, if I make it 2, it'll oscillate a little bit. And then notice it's gotten about half the distance to the desired point, because now the motor can output twice as much force, 2 times the error, so the error can be half as small. So if I keep increasing this, let's make it double it again. Now it should get even closer. But if you learned in math, if I just keep doubling this and try to get half my distance every time, I really won't ever get there. If I double it some more, again, it's getting closer and closer and closer, but it won't ever really reach the desired point. In order to do that, I would have to have a KP equal to infinity. And that's not possible because our motors really can't output the max force. And we can show that here. The max motor force is 1 Newton. And over here, the green line is used to represent the motor output. And you can see when I move this back and forth, when the green line turns red, that means we're maxing out the motor. And so the motor is only so strong, and that's realistic, right? Our motors can't input or output infinite force. So a KP of infinity or whatever humongous number still doesn't make our motors any stronger. I could make this 8,000, right? But all the motor's doing is it's taking this tiny error and it's bouncing back and forth in a crazy manner. This would be horrible on an actual motor. But 8,000 times this error is just enough to get it past our desired point, and then it sees it's too far, so it does 8,000 times the error and backwards, and it pushes back the other way and get these crazy oscillations. The motor's just maxing back and forth. You burn out a motor really quickly. So making KP humongous is just not the way to do it. So we're going to have to figure out another way, and that's why we add the integral control. Now the integral control is a way to always add up the error, and so that it will um, get us to the steady state value that we want to, or that desired point. Um, so just following along with the notes here, I'm going to increase Ki to 0.1, but before I do that, I'm going to hit the reset the car, because the whole time integral is Ki times the integral the area between our actual and our desired. We've been integrating for quite a while now while this thing has been running. So I don't want to just multiply that integral, which is right now being multiplied by 0, not making an effect. If I multiply it by some non-zero number, that huge integral is just going to shoot the car past our desired point. Maybe I'll show you that real quick. If I multiply by some number besides 0, that integral that's been winding up forever is now just going to shoot off. So that's why I really should have, I'm going to go back here and make this 0. So we're going to pretend like we don't have the integral. Anytime we really change the integral, where that integral's been winding up this whole time, adding up, I want to hit the reset car button, because it's just going to, again, shoot the car off. So reset the car, make it 0.1, and then now my integral controller's starting with a new integral that's adding up new fresh numbers. And notice that this time the car is getting closer and closer and closer to the desired value or desired position of the car. And we'll get there in just a little bit. It's taking kind of a while, but hey, it's getting there, right? And that was still with a KP of 1, not even 8 or 8,000. So not bad. I'm going to reset, and I want to do it again, but notice the colors that we see here. There's a color for KP and there's color for KI down here. The KP value, or the amount of force that comes from the KP term, is red. The amount of force that comes from the KI term is green. So right now you can see it's all green. So if I hit reset, you notice originally it's red because the proportional is what's really pushing it. But as it gets closer, KP times a small error gets smaller, but the green gets larger because we're adding up more error, or the area under this curve between the blue and the gray lines. And so eventually, as we integrate that area, then we get to a point where it's Ki times that area equals the force that's pulling us backwards. And so it will get the area to go to 0 and balance out the pull of gravity, so we get to where we want to be. And now that the error is equal to 0, this green line won't get any longer because we're adding zeros now, because the area is 0. So that's how KI works, or integral control. It's to get us to where we desired, or where we want to go, but we have to be careful. Just like we noticed when KP was really big, it made a lot of oscillations. That can happen too if KI is really big. Now again, I'm going to change this, and if I change this to a different number, it's going to take that interval that we added up times a different number. It's going to shoot off. So I'm going to hit reset car, and I'm going to make this really big. Let's say 10. Now, whoa, what's going on? Notice here the colors we're seeing is green is pushing it back, red is wants to push us forward. Our KP and our KI terms are fighting each other because we are integrating some errors that make it want to push far past our desired point. KP wants to pull us back. And so when we add up the area and finally get Ki to agree and go negative, KP will push us back, push us too far back. And so now we're getting oscillations, and honestly, it's just getting worse and worse and worse. We can see it again if I reset the car from a very small position. Again, you can see it quickly starts oscillating. It just gets worse and worse and worse. So another caution with integral. If we increase this number too much, then we just get some pretty bad oscillations, and that's not good. Let's try it again with, let's reset the car, and let's try it again with 1. I may have to reset again here. So KP of 1 even is just too much. You can see the oscillations just get larger and larger every time. So maybe that's why KP of 0.1 is a good number. Yeah. Let's put KI back to 0. Leave KI at 1, and now let's talk about KD. What KD does is, KD is a derivative term, and it differentiates the difference between our actual and our desired. And so really it's kind of this gap, we're subtracting the two. And then it's taking that error and differentiating it. And so it's really looking at the slope. Right now there's no slope, and so 0 slope times 0 KD, we're not going to get much out of it. If I change KD to 0.1 and then reset the car, we'll see that what KD is trying to do, is add damping. Where basically, if there's a steep slope, meaning the car is moving too quick, then it will actually fight us and push backwards. Okay? So I'm going to hit reset car, and you'll see that it barely oscillates. And if you can see, the derivative term from KD will be in blue. So you can kind of watch for a blue arrow right here. Anytime we reset the car, when it used to oscillate for quite a while, now it doesn't oscillate much anymore. We can go back and look at it again, make KD 0, hit reset. And you can see it oscillates for a few seconds. But with a KD of 0.1 and hit reset, it dampens out much more quickly. And we can try experimenting. Let's make KD even larger and hit reset. And you see that, wow, that stopped oscillating very quickly. And that's what's one thing that's really cool. Again, we can control how much damping we get by changing KD. But like our other KP and KI, too much is sometimes too much. If we change this to too high of a value, like let's say 10, then I hit reset. Now notice, it's not oscillating, so we're doing a good job not oscillating. But oh my goodness, it is taking a very long time to get back to that same point where we were before, where it finally settles. So too much damping. Okay, we're almost driving with the brakes on. And if I move this around, oh, it doesn't want to move anymore. I think I crashed it. Maybe I'll refresh it. There we go. Let's start back over. So let's go to 0, 0, 1, 0.01, and then put it on slope. We'll make KD 10 again, and we'll try to move this around. Oh boy, I think that just crashes it. It does not like that large of a KD value. I wonder if I just go back to 0 if we behave again. No. So we'll refresh one more time. Let's make sure we can adjust stuff. Yeah, it seems to be working okay. So we'll reset this. So back to 0.1. Oops. And make this 0, 0. Okay, so in summary, what we need to understand is KP is kind of the main motor driver. That's what gives us most of the force, right, to get where we are currently closer to where we want to be. But we can't get there, usually we can't get there with just KP, so we have to add KI. And that gets us, so our error goes to 0, or our steady state error goes to 0, meaning where we're at matches where we want to be. And then lastly, the derivative, if we have a lot of oscillations, then that's used to kind of add damping or to kind of slow down oscillations. So if we can combine all three, then we can get a more optimal performance. So after tweaking and playing with some numbers for a while, I'm not going to reset the car. I'll just put in some numbers and let the car go crazy, and then I'll hit reset. But after playing with a while, it seemed like these three numbers were pretty good. And once the screen clears, I'll show you. So if I change where I want the car to be, oh boy, nope, that's crashing again. Oh boy, I think the website's frustrated with me. I can't control it anymore. Let's try that one more time. I'm going to refresh the page. Try 10, 3, 4.01. Let's see if we can, yeah, we can control it. I'm going to put it on a hill again. And yeah, notice that does a pretty good job. Oh boy, it's crashing again. Yeah. Oh, maybe I can just do this. I didn't know we could do that. Nope. Yeah, this is kind of acting funny. Well, try it for yourself. The link is in the notes, and try these numbers. And when you do, you'll see that I can move this slider back and forth pretty easily, and it'll follow pretty well. Let's see if I really just hate having a high KD value. Yeah, it's just crashing. So, well, it is just a website, just a Java app. So it is what it is. But again, to recap, KP is our main motor driver. That's the main kind of muscle of the controller that gets us to where we want to be, but it can't get us completely there. So we add an integral controller, and that gets us to our steady state. Error goes to 0, and then KD adds damping, so that way it doesn't oscillate as much. You see, wow, that looks pretty good. So anyway, try this out. The link is on the notes, and you can play with these numbers. Again, this combination gives a pretty good value. You can even try changing the motor force if we are willing to cough up the expense and buy a more expensive motor with greater output. You can see we can have better control gains and get even closer to where we want to go much more quickly. So I hope that was helpful and a little easier to follow than just reading the notes.